Another indeterminate form we're going to look at is if we have infinity over infinity. We can apply L'Hopital's rule with this as well. So if we're taking the limit as x approaches a of some f of x divided by g of x, and when we evaluate that limit, if we get out infinity divided by infinity, and plus or minus doesn't matter here, we can also see negative infinity coming out, then evaluating that limit, we can apply L'Hopital's rule that says we can take the derivative of the numerator and denominator separately. And that could evaluate the limit for us. So we're taking this limit as x approaches a of f prime of x divided by g prime of x. Okay, so same rule as the last one, it's just a different indeterminate form that's coming up. So this limit as x approaches infinity of 3x plus 5 over 2x plus 1, we actually saw this earlier in our infinite limits video, and we talked about this horizontal asymptote at 3/2. We also did that special like dividing by 1 over x in the numerator denominator. Let's take a look with L'Hopital's rule. Because the idea is if I plug in infinity at this point, so 3 times infinity plus 5 is still just infinity, 2 times infinity plus 1 is still just infinity. So with that, we have this indeterminate form. So what I can do is take this limit as x approaches infinity of 3x plus 5 over 2x plus 1, and applying L'Hopital's rule, we're still evaluating the limit as x approaches infinity. In the numerator, we would just be left with a 3. In the denominator, we'd be left with a 2. Which means we don't have anywhere to plug in for x, so this is just 3/2. So as a refresher, I'm going to scroll back here a bit, just so you know, as I flip through the screens. Here we are. There was all the work we did to get to that same exact spot. So either with the horizontal asymptote or that special multiplying and seeing where zeros were coming out. With L'Hopital's rule, it's a little bit shorter. Maybe I think our equations were slightly different, but similar enough that the property comes through. Okay, with this one, we're evaluating the limit as x approaches 0 from the right. And to know that these limits are going to infinity, let's just take a look at the graphs. So let's just graph natural log of x. If I'm approaching 0 from the right-hand side, what we can see is approaching 0 from the right, we're going down off to negative infinity. So up there we would be getting a negative infinity out, and evaluating that limit as x approaches 0 from the right of cotangent of x, we would be seeing a positive infinity coming out. So just to the right of 0, we'd be going off to positive infinity. So like I was saying, positive, negative doesn't matter. It's just having infinity over infinity is going to be our indeterminate form. So we're evaluating the limit as x approaches 0 from the right of natural log of x over cotangent of x. And we're going to apply L'Hopital's rule. So we're still taking the limit as x approaches 0 from the right. Derivative of natural log of x is 1 over x, divided by derivative of cotangent x is negative cosecant squared of x. And if I go ahead and plug in 0 at this point, so 1 divided by 0, well, that's just undefined. Even if I move that x to the denominator, we're getting a denominator of 0, which I don't like. So negative x cosecant squared x. So in both of these forms, it's coming out undefined. It is not an indeterminate form, just having like a number divided by 0. That's undefined, not indeterminate. So this isn't saying to use L'Hopital's rule again. We might get to that point, but at this point, I'm not applying L'Hopital's rule. I'm just having issues because it's undefined. So what I'm going to do is, so I moved x, trying that, I'm still getting 0 in the denominator. What I'm going to look at next is I have this cosecant squared x. So I'm going to re-express that in terms of sine. So what I'm going to do is change this around. I'm just moving things. I'm going to go ahead and bring that negative out front. Or, yeah, negative out front. And still have a 1, x. And then cosecant squared would be the same thing as 1 over sine squared. If I multiply the numerator and denominator by sine squared, then what I'm taking is the limit as x approaches 0 from the right of negative, let's go ahead and put that in the numerator, negative sine squared x over x. Okay, so we re-expressed it a little bit. Instead of cosecant squared, we're now using sine squared. So now I'm going to try to plug in 0 again. So this would be negative sine squared of 0 over 0, which I still don't like, but sine of 0 is 0, so now I'm getting an indeterminate form. So now I can go L'Hopital's rule again, now that I have a 0 divided by 0. So that's a key piece. In order to apply L'Hopital's rule, we need that set up. So we can go L'Hopital's rule. So I'm taking the limit as x approaches 0 from the right. And let's see, some chain rule here. So we'll have negative 2 sine x times the derivative of sine x, which is cosine x, all divided by derivative of x, which is just 1. So we're taking negative 2 sine of 0 times cosine of 0, which is perfect. Nothing's ending up undefined here. We're not getting to an indeterminate form. So we can just evaluate this with the negative 2 times 0 times 1, which is all just going to turn into a big old 0. Whew. That one had some stuff where I like this as an example because it shows other methods of simplifying and moving things around, either to get to an indeterminate form so we can apply L'Hopital's rule, or it could even just be simplifying things so that we can actually plug in 0 to evaluate. And all of this to end with, just keep in mind the cases where you don't need L'Hopital's rule. What we should always do, and what I try to do with all of these, is always try to plug in first. So like plugging in x equals 1 here, so like a 1 squared plus 5 over 3 times 1 plus 4. Well, that's a 6 over 7, and we're done. That evaluates the limit right there. What we want to be careful of are these cases where an indeterminate form comes out, and then we want to do something about it. We also saw cases where we would simplify the function a bit first, like maybe you could factor and cancel out common factors. There were different things we could try first. It's just now when you get to these indeterminate forms, instead of having to jump to the graph to evaluate, you can apply this L'Hopital's rule.